Thank you so much. Thank you for having me. Really happy to speak at this Workforce Community Initiative. So, gonna begin the presentation by saying the current reality in scientific campaigns, where we have disconnected data workflows and users. Right here, I'm showing on the right hand side. I'm showing some different instrument facilities where we have different instruments like a microscope or a 3D printer or image or cameras taking pictures of your experiment in science labs. And then these instruments, they are generating data, sending data to a compute facility where they that needs to run HPC simulations or AI model training and others. Um, and the thing is, the problem is that there still needs to happen lots of manual orchestration across facility, manual and ad hoc data movements. In AI plus HPC instruments, it's creating even more complexity in this setting. And we are needing to have scientists, instead of focusing on their domain science, on their scientific experiments, they need to work as a system and data integrators to move data around and to integrate those different systems to work together. Right. So in a convergence landscape, we want to converge edge, cloud, HPC, scientific instruments, and AI, where we would have AI models, simulations, and experiments to enable intelligent prediction, automation, and integration. We want to enable multi-facility integration and to aggregate and stage distributed data and execute large-scale simulation and analytics. Instruments in Edge to capture and stream experimental data, and continuous decision loops to drive continuous and adaptive decision making. So we are in this towards autonomous science at scale, from these old static workflows to intelligent and agent-driven systems, where we can do continuous and closed-loop experimentation, integrating HPC, AI, and instruments, and accelerate discovery cycles from years to months while ensuring reproducibility and openness. So we believe that we can have laboratory ecosystem, workflow orchestration, distributed facility, data management, provenance management, all being integrated by AI agents. So this is the vision where agentic scientific workflows, from single agent actions to collaborative and autonomous workflows. These agentic workflows, they are goal-driven, adaptive, autonomous, and they provide autonomous decision-making, dynamic workflows, task definition and execution, multiple specialized collaborating agents. They could be planning, orchestrating, and coordinating between agentic and non-agentic tasks, humans, and federated systems. Here, on the right-hand side, I'm showing this this life cycle of a workflow, where we do workflow design, workflow execution in the computing continuum from the edge, cloud, and HPC, and workflow data analysis. And here, in what I'm calling this intelligence layer, we have report generation, workflow design generation, infrastructure discovery, and many other capabilities that these will be orchestrated and executed by AI agents. And in the center, I'm showing this human plus AI in the loop, where we have the scientists plus the AI agents interacting and helping each other. One guy, the human guiding the AI agents, not doing knowledge sharing and requesting tasks and analysis. A vision on this agentic AI workflows. We published this year at Works. We got the best paper award, the distinguished paper award at Works, the workflows workshop at SC this year. So this is all very exciting and promising. But if you play a little further with those AI, this Gen AI services such as ChatGPT or other LLM services, you're gonna start seeing some, at least to say the least, weird things happening. So here, the LLM is saying that 6.9 is less than 5.11, and if you go to ChatGPT right now, you're gonna see it's written there in very small letters that ChatGPT can make mistakes, and in fact, we know that Gen AI is non-deterministic in nature, and hallucinations are very common, even in state-of-the-art models. So hallucination is not a bug. They're gonna happen anyway. It's part of this technology. Gen AI is an amazing technology, but we need to use it with caution. Otherwise, things can go messy, right? So here I'm showing an example of what I'm calling data flow contamination. So for instance, suppose that you have a workflow like this, right, where you have just regular tasks, normal tasks that we usually have in workflows. But you also, along with normal tasks, you also have agentic tasks, which are tasks that rely on one or more Gen AI service, like an LLM, for example. And here, this is showing that one result, like 3 is greater than 5, this is the output of this task is being the input of this other task, and because of this hallucination, the whole data flow is contaminated. So we need to address this issue. So how to make agentic scientific workflows more reliable? So how to enable reproducibility, agentic accountability, transparency, and other critical principles in science, and how to keep track of hallucinations, mitigate and remediate their downstream impact in agentic workflow. Spoiler alert, Provenance data management can help. So here I'm showing this Provenance data to support large-scale workflows picture. This vision of having Provenance data as a main integrator of different phases of large-scale scientific experiment has been proposed by my PhD advisor, Professor Marta Matoso, in 2010, around 15 years ago, where we can see all these different phases of a large-scale experiment being driven by provenance data, where we can integrate all these different pieces that compose the experiment, all the way from workflow composition to execution and analysis, right? Here in the bottom, I'm showing the W3C model, which is being used by the workflows community or the provenance community as the main or the standard model to build the standard data model to build provenance data or to generate provenance data. So this is the way that I see the role of provenance in agentic scientific workflows. I believe that we have two main pillars that I'm calling provenance of agents and provenance with agents. With provenance of agents, meaning that we need to capture and contextualize all these agents' decisions, actions, and interactions within a workflow to enable traceability, accountability, and impact assessment. And the provenance with agent part, on the other hand, we are using this Gen AI technology, which I said that's amazing, right? We need to use it in a safe way as a natural language interface to provenance database to enable scientists to query and explore complex provenance data more easily and interactively. So provenance keeps agents accountable while the agents make provenance accessible. This is the way that I see provenance data in agentic workflows. So the fundamental concept is to use provenance as the glue to unify services, workflows, agents, and user interactions across federated scientific campaigns. Here we have the Edge-Cloud-HPC continuum with different services, distributed federated services like ad sensors, instrument drivers, brokers, database, file systems, cloud services, workflows, and simulations running on the Edge Cloud and HPC continuum. And the idea is that we should have provenance captured in all these different services, capturing to capture provenance data, and also this agentic provenance capture in these agents that are now steering or interacting with these different services. And all this provenance data is being capture integrated in a provenance database where scientists, users, engineers can run reproducibility analysis, root cause analysis, hallucination tracking, and monitoring. So we've been building this system called Flowcept for a while now, and the main goal is to unify workflow provenance data management into a single system and infrastructure. So Flowcept has a distributed, loosely coupled, flexible, and string-based architecture where we have provenance, domain-specific metadata, and energy indicator capture via code instrumentation and data observability. I'm going to explain this soon, and unified runtime data access from science labs to supercomputers. So the way that Flowcept works is by providing these observability adapters. And so, for example, if you already have some code or some use case that uses MLflow, TensorBoard, Dask, Redis, SQLite, or these other systems, the way it works is by Flowcept provides plugins that you can attach to these existing systems, and then provenance data will be captured while these systems run. Or if you're not using any of those, but you have generic Python functions, or if you're training a PyTorch model, or if you're now developing MCP-based agents or Academy agents that I'm also going to explain later, we have ways to instrument those agent actions. And whenever the agent runs MCP tool or runs an action, we're going to be capturing provenance data and publishing and storing data and sending data to a streaming hub that's composed by Redis, Kafka, and Mothka. Mothka is the streaming service system developed by Argonne. And then we have what I call the provenance keeper that subscribes to the streaming hub and then creates this raw provenance data and ingests in a provenance database that users can run provenance queries or deploy some Grafana dashboards or run queries and query APIs. And now we are introducing this provenance AI agent where the agent will allow user to query the provenance database or directly query the streaming data the streaming provenance data being sent to the streaming hub. So why provenance with agents? Right. So I hope that by now you understand that workflow provenance is essential for reproducibility, anomaly diagnosis, and experiment understanding. And this is especially even more important in federated Edge, Cloud, and HPC workflows because these workflows are highly distributed, highly federated. So you know that problems will happen. So you need to have a way to keep track of these distributed workflows running. And now with adding these Gen AI services that they hallucinate, it's even more critical in agentic AI workflows. But the problem is that at scale, provenance data are hard to analyze. In current tools, they rely on custom scripts, structured queries, dashboards, or complex graph visualization tools. And our goal is to bring scientists closer to runtime provenance data through natural language interaction. So the need is to democratize access to large provenance data via natural language during and after the workflow runs. There are several challenges. I'm listing a few of them here: heterogeneous data in multiple workflows, designing a domain-agnostic system that generalizes to different scientific domains, large streaming data across the Edge, Cloud, and HPC, Gen AI hallucinations, and limited LLM context windows, even with the Edge models. I'm highlighting this in red here because this is something that is important in our architecture because we cannot simply get the whole provenance data ingest into an LLM prompt and ask it to analyze my provenance data. That will never work because the provenance data can be gigabytes of data depending on how granular your provenance tracking is. So our solution relies on metadata and schema-driven. And to have the LLM agents generate the provenance queries in a modular architecture and evaluation methodology. So the basic idea is that we have running workflows generating massive amounts of provenance data at runtime, and then we have the agent, the provenance agent, using RAG techniques to query the provenance database, and using an LLM service where the human, the scientist, can just issue natural language live interaction queries. So we have a provenance query taxonomy and evaluation methodology where we have where we build a ground truth data set with query plus ideal answer per class, and we systematically tune the prompts and RAG techniques across diverse query classes. And this the goal is to avoid ad hoc and overfitted fine tunes in the prompts. And this helps us building a domain agnostic data set aiming at generalizing across various domains. This is the agent architecture, the Provenance agent architecture, where we have the context manager that connects to the streaming hub and builds the internal context. These are the dynamic schema and value. I'm going to explain in the next slide about this. We also have a to-router and monitor that, depending on the user query, it's going to route across different tools in the agent. And all tools and LLM calls are recorded as provenance data. So we are using our own provenance system to record data, record the interactions with of the provenance agent. This is the metadata and dynamic schema query-driven approach. We don't do any new training of the LLM itself. We only fine-tune the prompt using prompt engineering and RAG techniques. The LLM only knows a compact and token-efficient schema, not the actual provenance data. We never send the actual provenance data to the LLM service. The prompt structure of a query, it includes the static common fields, dynamic domain fields, and guidelines plus custom guidance plus few shots. So here on the right-hand side, I'm showing the dynamic domain fields, where we have these used and generated fields here, and this is where the whole domain part goes into. So here, this was run on a computational chemistry workflow, so we can see some smile string from this domain, from the computational chemistry domain, and also some values generated by these particular workflow tasks that generated bond energy, enthalpies, and free energy. These are domain-specific values. Whereas everything else that is in gray here, these are the static common fields, meaning that these are common in all other domains, in any domain. This provides for high scalability, meaning that our approach scales with workflow structure, number of activities and parameters, and it's independent of the number of workflow tasks, and supports sensitive data, since we never send the data to an LLM service. So now the provenance with agent part. So we have a systematic capture and representation of agents' decisions, actions, and interactions, and their effects within the workflow, supporting the agent behavior is traceable and accountable. This is the definition of what we're calling agentic provenance, and we published this at eScience this year. So whenever an agent runs, its metadata are recorded and linked with the broader workflow provenance using W3C-Prov, our standard model, and MCP concepts for agentic workflow. So here I'm showing a very simple example here where we have an MCP tool, and everything that the user needs to do is to decorate this particular MCP tool, and then everything will be recorded in the provenance database. This is the provenance graph that was generated by using the when you use our system to capture provenance, it's going to generate a provenance graph like this. So we can record, so we can trace back. For instance, this was the particular agent that ran this particular tool, and then we can link to the input data that was used, the output data that was generated. We can navigate in this provenance graph, so we will have deep understanding of every single action and which LLM was used and which version of the LLM prompts, if you're using LLMs, of course. So we keep track of all this while you are running your agentic workflows. Now moving to the experimental evaluation. So I ran this experiment with by building a ground truth data set, building 20 created natural language over a synthetic simple workflow. Here I'm showing this. This is a very simple workflow that's just doing some simple mathematical functions. And then I used LLM as a judge strategy to evaluate the generated query quality, not the result set. And our goal is not to pick the best LLM, but to test if our approach generalizes across different LLMs and different domains. We tested the open source models like Llama and GPT, Gemini, and Claude LLM models. And we fine-tuned the synthetic workflow and evaluated on other real workflows. So these are the main findings. The first thing is, since we are using an LLM as a judge approach, we've evaluated two different LLM judges. So the first goal is to make sure that they are agreeing with each other. These two judges are they are providing similar scores, and they were in our tests. But we also found that GPT and Claude, they provide strong performance. Llama and Gemini, they had higher variability. And we found that when they use the queries were graph queries, like when we need to traverse a very long graph path in the provenance graph, this was when the LLMs failed the most. So this was very hard for the LLMs to generate meaningful or correct queries when running graphs. And we found that no LLM is one-size-fits-all because some graph query classes work better for certain LLMs, and whereas others work better for Claude, for instance. And guidelines, schema, and few-shot examples, they provide large boosts with low token overhead. And the response times stayed within interactive bounds at just about a couple of seconds, meaning that the user would issue a natural language query and the result would be within a couple of seconds to the user. And we also found good generalization when running on a real workflow. I'm running a little bit because I'm hoping that I can show a video on our use case that we demonstrated all this in an agentic workflow for adaptive control of metal 3D printing. So at DOE, the Department of Energy in the United States, we have some of the best instruments or scientific tools in the whole world. And for instance, we have at ORNL, we have Frontier, which is one of the main the fastest supercomputers in the world. We have amazing plant facilities that can analyze images. But in this use case, we are using the manufacturing demonstration facility where they can print metal pieces that are huge metal pieces, like the size of a whole room here. These arms are on the size of a whole room. They were printing replacement parts for like the stuff that they can build replacement part for airplanes, for example. So this is the Edge-Cloud-HPC infrastructure for additive manufacturing at Oak Ridge, where we have the 3D printing facility in here, and then 15 miles apart, we have the HPC facility with Frontier and other cloud services. And this is just to show how geographically apart we need to communicate and do live streaming from site A to site B. So current experiment workflow requires manual configuration with on-prem simulation and fixed decision criteria. So there's no much room for fine-tuning, runtime steering or runtime fine-tuning. And our work enables cross-facility experiments and explores AI agents for autonomous decision-making and helping users to steer the workflow at runtime. The agents make informed decisions based on human guidance. That's the main important part, sensors and simulations. The agents help you if you have ever been in a situation where you blaze your plans on simulation only to find that they miss crucial physics. So this is where you can help the workflow, to guide the workflow to make runtime decisions and make it change during the execution. Some logic there, some logic, there's some logic to add, but there's no time to change the code, and something is going wrong, but you don't know what or why it went wrong. Okay, so I'm gonna go to the demo part. So we presented this at the DOE booth this year at Supercomputing. Let me restart. So we have here 3 different agents interacting here, working. And initially, the first thing that happens, we have one agent that we call the human interface agent that helps the user define the experiment parameters to run this workflow. So here the user is just defining some parameters to run the 3D printing workflow. Everything's correct, so let's start printing. When this happens, when the user says everything is ready, let's run, there is lots of messages that are sent around from the 3D printer to OLCF, where we have Frontier, where we have the supercomputers. And then we run the workflow. And while the workflow is running, the user can ask the Provenance agent to ask questions about their workflow. So like, how long since the last control decision? How long ago was the most recent control decision? So these are some provenance questions, or what are activities in this workflow? Then we get the results. Which activities are associated with agents? So we are seeing these are the actions that the agent executed. For the choose option activity, which are the inputs and outputs. There's a little messy here, but the idea here is that the user can deep dive and inspect every single internal action in this workflow. Just showing different exploration of provenance analysis in this workflow. So yeah, I'm concluding, just showing some next steps for this work is that we are integrating across various DOE initiatives, including the American Science Cloud and Orchestrated Platform for Autonomous Labs, OPAL, where we're going to have several different agents and across different infrastructure, from closer to the scientific facility, going to the cloud and going to the supercomputers, also using the public cloud. And then these agents will be running different AI services like LLMs or multi-models or simple regular workflows. And we will have humans fine-tuning this workflow, including fine-tuning the training of an AI model on supercomputers. And we're going to be using Academy for multi-agent orchestration, S3M, to ensure secure data transfer across these facilities. And Flowcept will be capturing the provenance all the way from the raw data until the reports generation to the user here. So final remarks, provenance of agents enable trust, so we can capture the agent decisions, interactions at provenance, as provenance enables accountability and transparency and reproducibility in workflows. And provenance with agents, we democratize access by leveraging Gen AI to help users access complex provenance databases. And we tested in different real-world scenarios, in the 3D printer scenario, in the computational chemistry scenario. Also, we are running now with plenty analysis and showing that our approach holds, despite it was trained on very simple workflow, in a synthetic workflow. It's generalizing very well for more complex scientific workflows. And we know the LLMs, they add to the scientific analysis toolkit but I don't believe it's going to replace years of development of existing methods. So that's it. Thank you so much for attending this talk, and this just to acknowledge some of my main collaborators here, including people from Oak Ridge National Lab and Argonne National Lab. That's it. Thank you so much.